तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We will discuss and continue to discuss about the high electron mobility transistor. Structure of the device, as I pointed out in the previous lecture, is semi-insulating substrate, undoped gallium arsenide. Notice there is this red another color layer added there, which is undoped aluminum gallium arsenide, and then heavily doped N+ layer. I just pointed out last lecture itself that this layer here is introduced, a thin layer of 20 to 50 angstroms depending upon applications. Mostly it is about 20 when you want 20 angstroms when you want high transconductance. Okay, we will see that later. But so that is a thin layer to ensure that the electrons here, the dashed line is showing the electrons, those electrons do not see the effect of these dopants. There is a layer undoped which does not have the impurities. So, to prevent the scattering, coulombic scattering, electrostatic scattering by these dopants here, an undoped layer is put gas. But still the notch is at this point. The notch is at the point at which there is a change from gas to gas. Okay. And also you can see the what we have here is N+ source state contacts are formed by allowing gold germanium on the substrate. The electrons are transported through the gallium arsenide region where doping concentration is very low. These are summing up what we discussed last time. At low temperature one can achieve very high electron mobility because ionized impurity scattering is rock bottom and mobility is well in excess of this. I just put excess of that because these numbers keep on updating every year. So, even 10 to the power 6 people have reported at very low temperatures. So, very high mobilities at low temperature. At room temperature, of course, the limitation is from the lattice scattering. So, about 8500, that will be the thing that you get in the gallium arsenide which is undoped. Okay. Now, what we said also yesterday or in the previous lecture was the energy band diagram, conduction band going up like this. This is a doped aluminum gallium arsenide layer and this is a thin undoped aluminum gallium arsenide layer, then the notch, then this is the well or the notch in which electrons are confined. What we are trying to point out is that these electrons are not just dumped there, they are actually having quantum states which has to be satisfied. That we just quickly go through that today. Just if this were a quantum well, instead of a shape like this, if it is an infinite quantum well, a flat bottom there, then what would be the distribution? That is what we are seeing, and the solution or equation that governs the state and the energy of these electrons is the Schrodinger equation in general. Wherever there is energy and potential, take these values. Okay. For a particle trapped in a potential well, the energy levels permitted are obtained by solving this equation. Whenever you want to solve an equation, proper boundary conditions. In practice, it is a finite well with a potential, the boundary which is about depth is V naught. The potential is V is equal to V naught here, V is equal to 0 here. A simpler solution which gives a good idea about what happens is obtained by an infinitely deep potential energy well boundary. It is not deep, it is infinitely deep. Okay. Please note that it is deep, depth is from here right up to infinity it goes, which is not a practical situation, but if it is high enough, it looks so high for the electrons, it looks it cannot mount through that. Okay. So, in a finite boundary it is like this. In a classical particle, if a particle is here in the potential well, it has no chance to cross this barrier. A classical particle we say it will remain all through its life here, okay. Whereas, unless it gets an extra energy to go through that. Whereas a quantum mechanical concept, the difference is that these particles which are look also like waves, behave like waves also have some probability that they can be found here, provided they are finite. If infinite, of course, there is no probability that the wave function can overlap into this. When you say the wave functions overlap into this portion outside this well, is that there is a chance that some of the electrons may be there. If there are hundreds of thousands of electrons, few of them may be there. That is a chance, that is a probability. That is implication, that is the difference between a classical particle and a quantum mechanical particle. So, now quickly running through the solution that we have discussing last time. In the region where this potential V is equal to 0, okay, you substitute V equal to 0 in the Schrodinger equation, you get that equation. T squared psi by dx squared plus 2m by h squared E into psi of x, where psi star or psi square is the probability of occupation in a small volume. You cannot say probability of occupation at a particular point, it has to be a particular region. If it is one dimensional, it is delta x, if it is three dimensional, delta v. So, that is the probability. So, psi star squared into delta v is probability in that volume, psi squared into dx dy dz integrate over the entire volume, probability is 1. The chance that you find it somewhere here in this well, that will be 1. So, that is the equation which govern some of these things. Now, you can see that instead of E minus V, I have just put V E there, because that is the equation within the well. So, you have to solve the Schrodinger equation within the well with the boundary condition psi is equal to 0 at x equal to psi is equal to 0 here, because this boundary is high. That you are telling is beyond that point probability of occupation is 0. Similarly, beyond this, I put it to the right, it looks like double L, but it is one L there. Beyond this point, the probability of occupation is 0. Probability of finding is 0, that is psi is 0. So, you solve that equation with those boundary conditions, psi is 0 at x equal to 0 and L. Now, this is a second order differential equation. So, solution will have sin x and sin k x and cos k x terms, where k is actually 2m by h square, d square psi by d squared plus okay, k squared into E. So, k is root of that. So, that is the thing. So, solution will have sin k x and cos k of x, but cosine function cannot exist, because at x equal to 0 cos function is not 0. As x equal to 0, it must be 0. So, you write the solution, though there are sin k x cos k x terms, you write only this, a maximum value in sin k of x. Okay. Now, here k is that root of that quantity, this quantity 2m E by h square. E also is there part of k. Okay. 2m E by h square, for root of that, that is 2m E by h bar. Okay. There is no pi here, but it is that quantity. Now, other thing that you would say is at x equal to L, also this term should go to 0. So, at x equal to L, psi of will be x, L will be 0, okay, if k into L equal to n into pi, n varying from 1, 2, 3. So, n are the eigen values, integer numbers which take 1, 2, 3, 4, 5. Okay. So, now, with that condition, psi equal to 0 at x equal to L, then k is equal to n pi by L, where n takes 1, 2, 3 values. So, now, k you know it is equal to that quantity, k is that quantity, and k also should be equal to n pi by L. So, from here you immediately know that n takes values 1, 2, 3. If the potential value is infinitely high, you will have infinite number of energy levels. So, corresponding to each n, you have got one energy level. That means, actually this is where you say the energy is quantized. You have got certain permitted energy levels with permitted psi, that is the wave function. You can call again psi 1, psi 2, psi 3, or phi 1, phi 2, phi 3, corresponding to E 1, E 2, E 3. So, E 1 is pi squared h squared divided by 2m L squared. Okay. Now, notice how much is this quantity depends upon that L, and the spacing between the two levels depends upon L. N is equal to 2, it is 4 times that E 1, but as L is made double, the width quantum L becomes longer, wider, the energy becomes smaller, the gap between them becomes smaller. If there is no quantum L, the huge region energy level is continuous. So, that is why in a conduction band where no quantum well, the energy level is continuous. L is actually tending to infinite, the energy difference tending to infinite. Okay. Continuous energy permitted levels are there, but the moment you have, like in the case of a heterojunction, you have a potential varying like that, you have got a finite L. Okay. In the case of in the case that we are discussing, that L is actually notch width, but the notch is not flat, it is just moving like that. We cannot say what exactly is L is, it is somewhere 50 to 80 angstroms, very small value. So, this is the understanding that we have got. So, energy is quantized, only certain values of energy are allowed, E 1, E 2, E 3, E 4. Okay. The integer n is quantum number, the particular wave function psi n corresponding to E n. Okay. They define the quantum state of the particle. When they say quantum state, psi and E are the ones. These are of course the terminologies that are used. The understanding finally is there are, you do not permit all the energy levels in a quantum well, there are only certain levels for one electron that is considered. If there are number of electrons, they will tend to go into that particular E 1, that E 1 will spread into a sub band. Similarly, E 2 will spread into sub band. Okay. So, you have, instead of having continuous energy levels, you will have sub bands which are seen. Okay. Now, this is whatever we have set in equation. See the psi 1 or phi 1, I just called phi 1 to, instead of saying psi for wave function, phi 1 is a particular n equal to 1, E 1 is at n is equal to 1, corresponding to that the wave function is like this, x equal to 0, psi is equal to 0, psi equal to 0, corresponding to n is equal to 2, you have got full sine wave coming up. That is the wave function 3, it is like that. In all cases, the wave function is 0 here, 0 there, but the edges, and you can see the spacing here will keep on increasing. If it is an infinite potential well, infinite number of levels will be there and 0 chance for these wave function to come. What will be the case if there is a finite well? I am not going to solve that. Okay. It will take another 1 hour to solve that. In fact, you solve within the well by the same way. You solve also outside the well. When there is finite well, there is a chance that there is a probability that you can find these electrons on the other side. So, these wave shapes, wave functions will follow same, except this will not become equal to 0. In fact, what will happen will be, if you solve that, what you have to do is write down the equation for this region with the same 2 m E by h squared as k squared. Here you write the equation k squared is equal to 2 m E minus V naught, where V naught is the height divided by h bar squared, h bar squared. Solve the equation, and there should be continuity of wave function from here to here. We are now taking that there is a chance for the electron wave function to overlap into that portion. That is, there is a probability that you can move into that region. So, when you do that, psi continuity, you get psi for here, psi here, and psi must be continuous there, d psi by dx also must be continuous. Then what happens is like this. Just the purpose I am putting that, you have a finite potential V naught. Okay. Finite potential well. Generally, you can skip this, but I thought I will show this to you because how it is, because you will see that when you see all the diagrams about the HEMT, you will see those diagrams. Okay. So, this is the E1, okay, that is energy level corresponding to E1. If it is infinite, you plot it like that, phi 1 or psi 1. If it is finite, then the probability will not go down to 0, the probability will not go down to 0, it will go something like this. There will be some probability. The wave function phi 1 or psi 1, whatever you want to call it, I call it phi 1 distinguished from the general wave function, it will go into that region. A classical particle will never, you will not think of a classical particle being here. Once it is well, it is in the well. Okay. Higher energy, if you have E2, for E2, what you have for, what you have seen there is, it is like this. That is for infinite. Finite, you will have the probability of occupation here, and the whole thing will come something like this. Again a probability. Only difference is between this and this is, this region, extended region will be more than this region. As you go to higher and higher energy, more and more overlap will be there. Understandable. If the electron is here, chance of it finding it on the other side, climbing up that barrier, going up there is better. So, E2 will extend over a longer path, longer x direction. If you have still one more, it will be having even more going up there. That of course, you can understand a particle which is jumping up on the wave, on the potential hill, potential well, if it is at higher energy, then from there it easily can go to the other side by jumping up. That is the meaning of that. So, these are look like abstract equations, but they have the meaning in the sense that if it has enough energy, it can go up. So, how much it is up into this layer depends upon this height compared to the energy. So, if the energy is up, third level, very easily it can go to the other level, that will spread into that region more. Okay. And if it is 0, of course, it is everywhere. So, this is the general concept. Now, you can see. So, when you go to the finite well, you get that particular thing, and you have to solve also equation with E n squared pi squared h bar squared by, I think there is a, it is okay. Okay, that is all right. The same equation that we wrote previously for energy n 1 2 3, and V naught will is infinity, then m n star. If you want to talk of gallium arsenide, you replace that m by m n star, plus equation must be modified for a finite well, that is what I said just now. So, what you get will be the one that is valid for effective mass, and V naught actually should be changed to finite V naught. So, this we come back to that diagram that we have been drawing. So, now you can see instead of being like this, the whole thing is something like that. Okay, you have a potential well which is something like that. So, you will have a level here, you will have a level there, and you can see also that is E1 and E2. Okay. And the solution of course is much more complicated. I am not attempting that here at all. What I want you to notice is, because now it is a finite well, on this side it is high, on this side it is like that. You can see the wave function is not 0 there. That means what you are telling is, these electrons which are present in the notch have a chance to be here. If it has a chance to be here, okay, if the dopants are here, there is a chance for them to be scattered. That is why, to prevent that chance of getting scattered by dopants, you put this undoped layer here. That undoped layer is because of that. If it is a classical particle, you would never have thought that I should have undoped layer. After all, the doped layer is here and electron is here. but now there is a probability that it is here. And if the electron is here, furthermore chance it can slide into that layer also, and it not only goes there, it goes also into this side. See, it can see it is plotted even right into this region, that there is some variation here. Okay. So, what we are telling now is most of these electrons will be occupying this portion level, most of them will be confined into this layer, okay, because higher it goes up, it can go into that layer or spread out. Okay. So, as you keep on increasing electron concentration, it will go into this sub level here, which is not one level, it is a band there. So, now when you talk of number of electrons, it is not one level, it is a band like a conduction. Instead of having a conduction band continuous energy here, you have sub bands. So, the second sub band, first sub band. So, these terminologies, in order to explain some of these things, I went through those things, the analysis, okay, the understanding of that, because otherwise it leaves, at least it left me vague when I saw these diagrams initially. Usually we think of a conduction band as a continuous level, but why it is like that? It is a quantum well. Okay. So, that is why energy levels are not continuous. Okay. So, most of the electrons will be occupying the level E1. Large electric field present in the gallium arsenide, again the summing up that whatever we said, present in gallium arsenide severely bends the conduction band and forms a quasi triangular potential leading to quantum subwells, subbands. The large electric field gives us potential there, and it leads to this triangular quantum well, it leads to the subbands. That is what we say there. Okay. In a MOSFET, the first subwell will be filled first. Most of these will be fully, it is almost completely filled. This will be partially filled. Okay. So, the mobility, everything will be decided by this band mostly. There will be difference in mobility of the subband and this subband. You know that as you go to higher and higher energy, the mobility keeps on falling down into the higher energy band levels. So, mobility of electrons here is better compared to mobility here. From this point of view, you would not like to dump electrons into this subband. If there are many of the electrons which are resting here, the average mobility will fall down. Okay. This we have seen earlier, when you increase the concentration or energy, it can go to mobility. In increase the energy, the mobilities are reduced, like scattering from one level to another level. Okay, that is easy to understand that way. The second subband at energy E2 is partially filled generally. The inset shows the wave functions here. In fact, I was not able to provide us the figure caption for this, so I have given it the next page. That is next page, the figure caption for this, the whole thing. Okay. Now, the extent of electron concentration depends upon delta E c and the doping concentration in L gas. The electron concentration here depends upon how much band bending is there. The band bending depends upon the doping ratios. In homojunction, Nd Na divided by Ni squared, logarithm of that into Vt. That is what we say, it depends on the doping here in this level. Here it is undoped. So, higher the doping, more will be band bending, plus delta E c. We saw that the total band bending here or total potential drop is equal to VBA what you get for homojunction plus delta E c by Q. That additional drop is there. So, that is what we meant by saying extent of electron concentration depends upon the band bending, which depends upon delta E c and the doping. And delta E c depends upon x, that is the mole fraction. Higher the x, higher will be the delta Eg. Higher the delta Eg, 0.64 times delta Eg is delta Ec. That is another aspect. So, we think we can confine as much electrons as we want till we go right up to x equal to 1. Instead of aluminum gallium arsenide, you put aluminum arsenide, but it does not work out that way, because when you add more and more aluminum, somehow there seem to be defects being introduced, and people have called those defect centers as some dx centers. This is a name that is called, I do not know why they call that by that name, it is a defective center, which are trap centers which tend to trap electrons, and the performance of the HEMT suffers from that, number 1. Number 2 is, okay, so that is why they limited x to about 0.3. 0.4 gives 0.5 E g delta E g, slightly lower than that, it is not linear, slightly going up like that. So, you get close to 0.5, 0.45 delta E g. So, you will have delta E c, which is something like about 0.3. 0.32 if it is 0.5, about 0.3 delta E c, which gives about 10 to the power 12 electrons per centimeter square. Okay. It gives about 10 to the power 12 electrons per centimeter square. So, okay, so that is the idea. Quite good enough. It is in fact larger than the electrons that you get in the inversor layer in a MOSFET. That is close to that, 10 to the 11 to 10 to the 12 per centimeter square. It is a charge sheet which is present there. Okay. Now, there is one more problem, technological problem. Apart from this higher aluminum concentration, introduces trap centers called DX centers. It also makes it difficult to make ohmic contact. If you recall, higher the band gap material, higher is the barrier height, N type particularly, higher is the barrier height, 2/3 of Eg, and its interference density is high. Higher the band gap, more difficult, higher the barrier height, less chance of it being making ohmic contact, better ohmic contact. Where? In the source and drain regions. There are two things, source and drain regions and the gate region. Gate region, of course, you would like the barrier height to be high. Drain region, where you make the ohmic contact, barrier height must not be high, it should be ohmic contact. That becomes difficult. Okay. In fact, you make that N plus there by gold germanium doping, but still all that happens in those situations is like this. See, you have a high barrier height like that. You dope it heavily, then the whole thing comes down like that. Lightly doped, heavily doped, this is Schottky barrier. I am sorry, MS contact, metal semiconductor contact, and that is a 5En. If you do not make it heavily doped, you will get high. Make this heavily doped, that is reduced quite a bit. How much it is reduced depends on doping and also a combination of these two. So, if this is high already, it becomes difficult to reduce it to the extent that you want. The moment it is not reduced to the very small values, it has a finite barrier height, finite, it looks as if it is a large contact resistance. So, in fact, way back in 1981, when I returned from US on technological know-how on gallium arsenide, we wanted to propose a project on gallium arsenide based devices. Immediately the experts here, so called, asked me, do you know how to make an ohmic contact to gallium arsenide? It is a valid question. I am putting this across to you, because everyone worries about making ohmic contact to gallium arsenide, higher band gap. So, gallium arsenide at that time was sorted out, and the answer was yes. Today, you go to gallium nitride, much wider band gap. You go to silicon carbide, the worry for the technologist is making a good ohmic contact. Schottky barrier, you just put a metal, make a Schottky barrier, absolutely no problem. The ohmic contact is a problem. So, you want to make a field effect transistor, that is where the difficulties are in the materials like gallium nitride, silicon carbide, etc. Same problem is present in aluminum arsenide. When you go to L-gas, when you go to X higher and higher, X higher and higher, wider band gap, barrier height more, difficult to make ohmic contact. So, that is what I am trying to point out. Plus, so that is the second problem. You put X equal 1 aluminum arsenide, that seems to be unstable. You tend to lose arsenic from that. So, that material itself is unstable when you just keep it open. or even raise the temperature slightly. With all those restrictions, okay, worried about the trap centers, worried about making ohmic contact for source and drain, and also stability of that layer. From all those considerations, you say, okay, 0.3 x 0.3 is sufficient for me, it gives me a fairly decent MOSFET. It is not enough if you are the MOSFET. You must be able to control the charge. See, what we said is, let me put that diagram quickly here, because I do not want to keep on moving into the diagram. What we said is, we can refer to this here like this every time, gallium arsenide, okay. Then you have the undoped gallium arsenide, you have the undoped gallium arsenide, okay, and then you have got the aluminum gallium arsenide. You may have a small layer put there which is undoped. N plus, this is N plus. I am just leaving this diagram so that we can take a look at it, undoped. And then you have got that, the moment you do that, that is a notch, where you have the electrons locked, and then you put an N plus layer here, source, you put an N plus layer here, which reaches right up to that point, and then a drain, you apply VDS here, then we current flow through that. That I mentioned it to you in the last lecture, because of the charges here. Okay. Let me just clean up it a little bit, because it looks a bit crowded here. So, I will just put it like that. Okay. Those are the electrons which are present, and that is the undoped layer, undoped aluminum gallium arsenide. At the moment they put this, they find the mobility is up, because the scattering is reduced. So, there will be current through this. To control that, how can you control this? How can I reduce this particular charge? I should be either reduce or increase. Okay. If I want to reduce that, I must reduce the band bending. Okay. So, how to do that? Of course, you must have another electrode which is put here, which is the gate. We will come back to this now. So, this particular charge you can reduce, because that is the notch that we have shown here. Okay. That is the notch. Aluminum gallium arsenide, and this is a situation where there is no gate. Okay. Just like this, and that is a variation. Forward bias voltage is equal to 0, thermal equilibrium situation, because and electrons are locked up here, of course, with E1 and E2 energy. They are not just staying there in as a gas there, though you call it as electron gas, 2D electron gas, it is quantized electrons. Now, when you forward bias this, see what is the polarity of this potential? Plus here, minus there, because this is plus, it has contributed electrons to this. So, that negative charges will be as electrons and also as the depletion layer charge. So, if I want to reduce this barrier height, I must reduce the depletion layer width. If I have to reduce the depletion layer width, how it is possible? Reduce the potential drop. Okay. And when you reduce the potential drop, that can be done if this is plus, this is minus, that is, this has a plus charge here, this is a minus charge. Here you have got all those immobile acceptors plus minus. This is where the potential is, and the plus is here, minus is here. If you apply a reverse voltage or forward bias, making this plus and this minus, just like take a p-n junction forward bias, the barrier height is reduced. Suppose, how much should I reduce the barrier height to make the charge equal to 0 there? That extra potential that was present due to the delta E c I was mentioning in the previous lecture. Charges are present in plenty here, charges are present in plenty, because this barrier height under thermal equilibrium conditions is more than the homojunction bias amount equal to delta E c by q. You reduce that by that amount, automatically charges come down to low value, that is this whatever was intrinsic point here will shift towards this point. Like in the MOSFET, if the potential drop in the p region is reduced, the inversion is reduced, you come out of inversion. Similarly here, the potential barrier reduced by forward biasing plus minus Vf, your charges reduced. So, you must be able to apply a bias across this junction to remove those charges plus minus. Okay. So, all these charges will be removed and put on there. Supposing I have a gate, if I apply a potential between the two forward bias, what is the meaning of that? I remove the charge and put on the other side, where the negative terminal is there. From this region, I take it to negative terminal, charge is more negatively compared to this. So, that is why you have got that charges removed, automatically potential is reduced. Now, a few things we have to see here. As the diagram is shown here, it is flat. If it is flat, what is the meaning of that? There is no potential drop in the Hall gas. If there is no potential drop in the Hall gas, what you say is only this portion of aluminum gallium arsenide is depleted, the other portion is not depleted. If it is not depleted, you have a worry in your hand. What is the worry? Conduction will take place due to these electrons, conduction will take place due to those electrons on this side here. So, when the MOSFET is operating, this entire layer must be depleted. That must be depleted. Okay. Look at this portion here. Above this, what does it look like? Above this, I do not see this portion at all, just above this only aluminum gallium arsenide. If I see, it looks like MOSFET. Source, drain, ohmic contacts, gate, Schottky barrier, N type region. Okay. So, this is a MOSFET. Now, in the MOSFET, you can deplete the channel completely by the built-in potential itself, okay, or apply a negative voltage to the gate, so that the entire channel is depleted. What is the voltage required to apply to the gate, so that this channel is fully depleted? That is the threshold voltage of the MOSFET, that is VBI minus VP0. VBA of this junction, not the VBA of this junction, VBA of the Schottky barrier minus pinch off voltage gives you the voltage that we have supplied to the gate to the pinch off completely. Okay. Now, if you just pinch off here, a situation will be there, the depletion layer will be just coming up to a certain point. Okay. Let me go back to the diagram and see. If you take this cross section here, this portion is a very crucial thing which you must watch. Easy to understand that portion because you are already familiar. Now, when the depletion layer is, so the field for this are in this direction, correct? The depletion layer due to the Schottky barrier gives rise to electric field in that direction. Now, let us say there is a depletion layer here. This you can ignore that layer, undoped layer, because very thin. Let us say the whole thing is doped, and this is total width, and there will be a small depletion layer here with plus charges. I am just ignoring that small spacer layer. So, that undoped layer is also called as a spacer layer or setback layer. Terminologies or setback layer. Just a name, I just forgot to tell you about that. It is undoped layer where it is spacing between the two, just a thin spacer layer. Okay. So, now I am just ignoring that effect of that because very thin. The depleted layer here will be having, see in this portion here you have got a this portion is the depletion layer where there is potential variation. Now, what we are trying to do is you put a gate there, Schottky barrier, whose depletion layer spreads right up to this point. You apply voltage which is coming close to this point. So, the field lines of this portion will be terminating on to the left hand side. The field lines here are terminating onto the metal. Depletion layer of the Schottky barrier is going like that. Whereas the field lines from here, where are they terminating? Down. See, this is the heterojunction that we have been talking so far. So, you have a MOSFET along with this heterojunction. So, this heterojunction has plus charge here, minus charge here. So, the field lines like this here, field lines like that, and once the depletion layer merges with that, you are safe. Okay. So, let us go into the analysis further. What is the situation now? So, if that point is clear, that is there are field lines, fully depleted layer is there, but most of the depletion layer is interacting with the gate, Schottky barrier, part of that is interacting with the p-n junction, field in the opposite direction. Now, ultimately you must reduce the field in this direction. If I reduce the field in this direction, what happens? This collapses, and what happens to that boundary? Let me draw that here. See, if I take n plus, if I take n plus L gas, there is a depletion layer here. I am just putting the diagram without all these things, and this is the gallium arsenide P minus undoped, and there is a depletion layer here. There is a metal here, that is the gate, okay. And there is immersion layer here. There are plus charges here. These plus charges belong to the depletion layer of the Schottky barrier. They are moving field lines in this direction here. That is electric field direction. These charges here belong to the junction, and those field lines are here, okay, E1, E2. For an outsider, that is, when you apply voltage between these two, the entire layer is depleted. Part of it is belonging to this, part of the depletion is belonging to that. So long as that condition is satisfied, it is okay. But now current flow will be through this. Current flow will be actually through this, because entire layer is depleted there. I drew it there because slightly more clarity is there in the diagram. Okay. Now, this is making contact with this particular layer. If I apply voltage between these two, okay, to the substrate there, you are applying, okay, you are making contact with that here, that is making contact with that, this contact. Okay. The N plus is making contact with this layer directly. Okay. Let us not worry about that. Let us see, suppose I make this more negative. See, what you require to do is, there is a drop here. If it goes all the way up to this point, the channel is pinched totally. That means, the entire depletion layer belongs to that. Okay. But you do not have to go all the way up to that. You will have to go very close to that pinch off point, very close to V B I minus V P 0, because part of the voltage is taken care of by the other junction. So, still we will say V B I minus V P 0 is the voltage required to pinch off the voltage, deplete the whole thing. Okay. Now, at this point, this is the depletion layer boundary. How is the electric field distribution now? You have all, the slides, they are all there, but I just put it on the board, so that you can just take a look at it. How is the electric field distribution? This is a junction. Okay. That is a 0 if I take, that is the peak point as far as junction is concerned. Then you have got the field coming like this. Let me just draw that slightly. I need more space there. That is the peak point. That is the electric field. Uniformly doped, because there is some charge is present here. Due to that, you will have some additional field coming up here. This is takes only depleted charge, because there are charges charge sheet here. This may slightly go up there to accommodate that. I am just leaving that out. And here it is coming down like that. What about the electric field here? That is negative. What about the slope of the electric field when I plot? Same. See, the slope of the field, electric field versus x is decided by doping here. So, the doping is the same thing. It is 0 here, comes down till you reach the boundary. So, this is E 1, that is E 2. This is 0. So, this is E 1 and that is E 2 here, that is in that direction, this is in that direction. Okay. Why I just pointed out this is, when I keep on depleting coming up to this point, what will be the potential distribution now? Okay. Now, let me just go into those. So, all these I just discussed now. I think I can come back to it later. So, if I have this particular electric field 0, if I move from here to here, there is a potential variation wherever changes are there. Wherever the field becomes 0, potential is not 0, it is minimum. If I go from here that direction, what will be the way the potential be? So, if I plot the potential, I think I have it already there, I will not plot that. If I plot the potential, if you go to that particular diagram, we will come back to this afterwards. All these analysis I will come back to afterwards. This is the diagram. See, the electric field actually is peak there, that is the gallium arsenide, this is the L gas, and this is the 0 electric field, which would mean the potential will actually be, this is actually the energy band diagram. See, the previous diagram what we showed was, it was coming like this, then flat. Instead of being flat, it is plus here, minus here now, energy band diagram. It is plus here, minus there, energy band diagram, depletion layer, plus here, minus there. Okay. So, this is the diagram when I applied the voltage up to this point, when I keep on increasing negative voltage to the gate, it will keep on moving up to this point, because till the depletion layer merges, there is a contact between this and this point. It is better to see in this diagram. Till the depletion layer reaches here, for example, when it is here like this, when the depletion layer is, I have the charges, when the depletion layer is up to that point and the depletion layer here is like this. See, as I keep on increasing negatively VGS, this particular thing is already there, correct, because of heterojunction. What I am doing is I am applying voltage between these two, negative. As I keep on increasing, what happens? Depletion layer keeps on widening. Okay, because there is direct contact here. This is virtually shorted out. You do not have transfer of electrons from here to there. This is the Schottky barrier which is acting. There is no control of this on this. It is all right. In fact, if you see this diagram here, okay, if I have this depletion layer, that is there whether this metal is there or not. Okay. So, when I apply voltage is negative with respect to this quantity, and if I keep on increasing that negatively, depletion layer keeps on moving. In fact, what will happen will be, over here you have got this already, that you have got, and over here what will happen will be, ultimately it will come with that, as you keep on increasing the voltage. Can you sketch the electric field? Plus minus, okay, electric field in that direction. Depletion keeps on widening like that, ultimately like that. Till that time you are not touching that charge. See, the interesting part here is, when you apply voltage to the gate, if the VBI is lower than VP 0, that is easy to understand. Depletion layer width is much smaller than A. If I want to deplete, I must apply negative voltage till that reaches and touches that point, this point. So, that is the point at which you have got this depletion layer. What happens beyond that is the question. If I increase the voltage beyond this point, this is the point at which the entire layer is depleted, and there is no contact here now. You do not have contact here because the insulating layer now. If the whole thing is depleted, even though this is there is nothing, but that is reaching into this. So, if I increase the voltage beyond that point, what happens is, the charge from here will be reduced. Okay. In fact, the charge from here reduced means actually depletion layer will fall. In fact, the voltage appears now from here and here, or here, actually it is here. So, you are removing the charge and putting on the other side. When you apply negative voltage, if you take a capacitor and apply negative voltage to some point, you are putting the negative charge and applying to the other side, more negatively charged. Negative terminal is more negatively charged. So, you are removing that and putting up there. When you remove that charge, automatically what happens? Potential barrier is lowers. See, the charge, the amount you remove, it is possible only by lowering the potential barrier, which means the depletion layer collapses. If the depletion layer here collapses, what happens to depletion layer here? Collapses. This charge reduces, but does it mean that this layer will open up? See, whole thing is you remove the charge from here, so which has reduced the depletion layer charge, which has reduced the depletion layer charge, but the total thing is insulated. Okay. There is additional voltage appearing between the two. So, that has gone into this layer. So, what happens is this boundary which is 0 field, moves to the right. You get the entire thing moving like this. Depletion layer narrowed, depletion layer here narrowed, here it is widened, the whole thing is insulated. So, you have got still that depleted condition, you still have, you can go on removing the charge. In fact, some more things, details about that I will continue in our next lecture. The idea is this: gate control can push the depletion layer to this region and can remove the charge from here. More negative I make, less charge, less depletion layer width, that is a forward bias, a pierce across that. How much I must apply here is equal to delta E c by q. Okay. We will discuss what actually is the threshold voltage of this MOSFET now next lecture.